point out, I mentioned previously, but I sort of mentioned it in passing, that our partial derivatives, f sub x and f sub y, are themselves actually directional derivatives. F sub x is the partial derivative in the direction of I, and f sub y would be the partial derivative in the direction of j. Okay. And of course, if we were in 3 space, f sub z would be the directional derivative in the direction of k. Now, we determined last time that we can calculate a directional derivative as just a dot product, because that's what I get from using the chain rule for the function composition of applying f to a line through the point P naught going in a particular direction. Okay. Now, notice if I do that, that's just the gradient of f is f sub x comma f sub y. And if I dot that with I, I'm dotting it with 1, 0, and I'm just getting f sub x. Similarly, if I take the gradient, whose components are f sub x and f sub y, and I dot that with j. Now I'm doing this in 2 space. In 3 space, I would be 1, 0, 0, and j would be 0, 1, 0, but the same principle holds. If I work out this dot product, I get f sub y. So the partial derivatives, f sub x and f sub y, are directional derivatives. They're just directional derivatives in directions that are parallel to the coordinate axes and pointing in the direction of that variable increasing. So f sub x is the directional derivative as we move straight forward, if we're in 3 space, and f sub y is the directional derivative as we move straight to the right. All right. I can also use the fact that I'm using the gradient to build the directional derivative, to use the directional derivative to tell me a little bit about the gradient. Let's just suppose I have a function f of xy, and I'm going to think of its output as being the temperature. Okay. So I've got some 2-dimensional floor, which I'm identifying as the xy plane, and if I'm at some point P naught, okay, and let's pretend I am a heat-seeking particle. So I'm standing here at P naught, and I want to go where there's the most heat. Well, if the temperature is a function of location, then if I move away from my location, the temperature could change. And if I'm a heat-seeking particle, I want to make sure that I'm moving away in the direction in which temperature is increasing, and not just increasing, increasing most rapidly. So I might be asking myself the question, in what direction does f increase most rapidly? In other words, I'm here. I want to move away from here, but I'm trying to figure out in what direction to go. So right now, my position isn't changing because I'm in planning mode. I'm trying to figure out where should I go. So the function isn't changing, the point isn't changing. What I'm looking at is varying u. In what direction should I go in order to have my temperature increase the most rapidly? Okay. Well, I'm going to use the fact that the directional derivative at this point, which is now the thing I want to maximize, I'm viewing that sort of as a function of u, holding everything else constant but changing the direction. I can calculate that as this dot product. But I know that a dot product is actually just a product of 3 things. It would be the magnitude of the gradient of f at P naught times the magnitude of u times cosine of theta, where theta is going to be the angle between u and the gradient of f. So I'm going to just, I'm not trying to put that on this plane. In fact, let me draw it up here. If I have a unit vector u, and then I've got the gradient of f at P naught. And if I'm not currently varying P naught, because I'm trying to figure out, I'm going to move my location, but I'm going to move it by going in the direction of U, and I'm trying to figure out what U is. So the gradient of F at P naught isn't changing, but this angle would change as I vary what U is. Okay, so that's kind of interesting, because notice this is going to be fixed. This is just 1, so it's times cosine theta. And if all I'm varying is what U is, what direction U points in, then I'm varying what theta is. If I want to maximize this, this will be maximized when cosine of theta is. Okay, so DOF at P naught is maximized when cosine of theta is maximized. But remember, if theta is the angle between two vectors, by definition, theta has to be between 0 and pi. Well, at 0, cosine of theta is 1. At pi, cosine of theta is -1. And in between, it takes on all of the values in between exactly once. So cosine of theta is maximized. I know cosine in general is maximized when cosine is 1. For a regular cosine function, that occurs infinitely often. If I'm restricting theta to be between 0 and pi, this is when theta is equal to 0. So I'm going to have that F will increase most rapidly if I choose U to point in the direction of the gradient. This is kind of cool. The gradient, which is a vector in the domain, so the domain of my function is in 2 space, the gradient is a vector in 2 space, but it points in the direction that I would need to go in the domain, within the domain, in order for my function to increase most rapidly. So, if I am a heat-seeking particle, I'm going to say, if the gradient of F at this point points in this direction, that's the direction I want to go in, because that's the direction in which temperature will increase most rapidly. Okay, so the direction of the gradient is the direction in which the directional derivative is maximized. Okay. Now, I kind of like using a heat-seeking particle when I'm thinking about that, because that way I really am just thinking spatially in 2 space. I could certainly be standing on a mountainside and be thinking of my function as giving me the elevation, but I want to remember that the gradient would simply be a vector in 2 space. So if I imagine the Earth at sea level as being a plane underneath this, where this mountain is, it's going to be the direction that I need to point myself this way. It wouldn't have any upward or downward component, but if this is the direction of the gradient, that would say if I put myself this way, that's going to be the direction now in which my elevation will increase the most rapidly. Okay, so if I look at the gradient of F at P naught, that of course is a vector. Vectors have magnitude and direction. The direction is the direction in which F increases most rapidly. In other words, DOF at P naught is maximized when U points in the direction of the gradient. Okay, and then what does that tell me about what does this tell me about the magnitude of the gradient? Well, if this is going to be maximized when cosine of theta is 1, when cosine of theta is 1, this is the value of that directional derivative. So the magnitude of the gradient of F at P naught is the maximum value for the directional derivative. And that directional derivative, that maximum value is achieved when the direction I choose is the direction of the gradient. So the magnitude of the gradient is the biggest rate at which f can increase in any given direction. Kind of cool. That's actually a theorem. That is theorem 15, okay? And that applies if f is differentiable, okay? So I probably should have stated that. If f is differentiable, this will be true. If f is not differentiable, then the chain rule really doesn't apply, does it? Right? So this whole dot product that we're getting was from taking the derivative of a function composition. All of this supposes that f is differentiable. So I should have stated that at the beginning of this section, but let's just state that now. Duff applies to differentiable functions. That follows directly from the derivative, because we said it was the derivative of the function composition f of r of s, where r of s was this line through our point in a given direction. And of course that function composition won't be differentiable if f itself isn't differentiable. So I apologize, I should have stated that when we started this section, but I didn't think to do that, so I will state it now instead.